Alright guys, welcome to another tutorial. This one's going to be on carbon, a central building block. Alright, so I've tried to work through this a couple of times. I'm not 100% sure how to teach it, so I'm going to do my best here and try and explain a couple things. If you have a background in physical science or a background in chemistry, then this would be far easier for you guys, and you probably don't need my help. But let's say you haven't taken chemistry, or you haven't taken physical science, or maybe it's just been a while. I'm going to try and reteach some of the fundamentals while emphasizing the important parts that will get you through this bio test. Alright? So for those of you that are just looking to pass this mastery test and maybe make it on the post test, I'm going to include most of a summary at the very end. So that'll be towards a couple, I don't know, last like 4 or 5 minutes of this video. Alright, but the first intro part of the video, I'm going to be doing a lot of background information. So if you really need to understand it, this is where you go. But for this particular video, because I have a feeling it's going to go kind of long, the last 4 or 5 minutes, I'm going to do a summary that ought to help you with the mastery test. Alright, so with that being said, let's go ahead and get started and see what we can do. First off, you'll notice on page 5 of your tutorial, it talks about the tetravalence of carbon. Carbon is going to be one of the most important elements on this entire table, and you'll notice that carbon's over here. Alright, it's number 6. It's a big deal. It's right there. Alright, and carbon is the existence of anything organic or anything living. So all living organisms have carbon in them. If it does not possess carbon, it is considered an inorganic molecule. Okay, so it's a non-living element. Or I'm sorry, non-living, whatever it is. If it does not have carbon, it is non-living. Okay, so what we want to know about is this whole valence idea. Valence is just how many electrons you have on your outer shell. And your goal is to reach a total of 8 for the most part. Alright, there are some exceptions, and there's lots of talks of electron shells and valence shells and whatnot. I'm going to do this in a really simplified way. Not all of it's going to be entirely accurate, and I'm going to let you know when I'm sort of simplifying things way too much. Alright? The first thing that we're going to do is, looking at our periodic table, you'll notice here to here, everything's written a little lower than the rest. Alright, these are called transition metals, and they have a really weird, well, not really weird, but they have an unusual way of finding valence. So these are going to be a little harder. It's a technique that's above the level that I want to go into for a biology class. So I'm going to skip this middle part on how to find these. Alright, to find the valence of these other ones, all you have to do is number your periodic table, left to right. Here's column 1, column 2, column, so skip all the transition metals, column 3, 4, 5, 6, 7, and this one over here with helium is going to be 8. Alright, so the purpose of doing this is because this tells me how many electrons are on their outer shell. Everything here has 1 electron on their outer shell. For example, hydrogen looks something like, this. You may not be able to see that too well, but the idea is you have an H. So here's your hydrogen, right? And your proton's in the middle. Well, dancing around that proton on an ovular path is going to be 1 electron, just 1, and that is because it is in the first column. Okay, second column, you've got like beryllium, Be on the top, so that one would look something like this. Here's Be, so it'll have like 1, 2. All right, so that's how you figure out how many valence electrons you have. Now, this whole shell talk, shells are a little bit different. For the most part, as a general rule, you're going to be looking to add up to 8 electrons in your shell. Hydrogen and beryllium are kind of different than that, but that's okay. We're going to talk about it with carbon in mind. Alright, so carbon has 4 protons and 4 electrons. What that means is that, well, 4 valence electrons. Carbon is one of those situations where we want it to add up to 8. Okay, that is our goal with carbon, add up to 8. You'll notice that we have a column 8. That means that these guys already have 8 valence electrons. These guys don't react with anything. You can mix argon or neon or helium with anything and they will never combine together because they're already full. It's kind of like the guy that ate like 50 burgers. He does not want your burger. It's just not going to happen. All right. So you want to get from your area in order to match these guys up and just, not need anything else. You want to fill yourself. You want to fill your electron shell. Okay, so for carbon specifically, you're going to want it to add up to 8, so you start with 4. That means that carbon is, just like on page 5 of your tutorial, tetravalent. Tetra means 4, so you need 4 electrons. You have 4, you need to get up to 8, you need 4 more. Okay, so that is what this entire page on page 5 is. Everything else is a little bit different, so you notice you have lots of different numbers, but that's what tetravalent means. Tetravalent really just means you have 4. That means that you need 4 more. You need to get up to 8 there. Okay, so we're going to go ahead and move on to page 6 in your tutorial and talk about its tetravalency some more. Don't worry about page 6. It's all pretty much already explained. So you have 4. You need 4 more to get to 8. They talk about that on page 6. Page 7 talks about covalent bonds. Okay, cool. So carbon is going to make a lot of covalent bonds together. The example that they gave you guys. Okay. They're just explaining covalent bonds in general. Covalent bonds are, again, strong, if you guys don't remember that from, I don't remember, lecture like 3 or something like that. But covalent bonds are fairly strong. And they're going to hold things together pretty well. Carbon is going to do a lot of covalent bonding. That is one of its skills. It happens to do a lot of bonding with things. Okay? Let me make sure there's nothing else on page 7 that we need to worry about. Okay. We're going to go ahead and move on to page 8. Now, carbon can form a lot of different bonds, so just keep in mind it does have 4 valence electrons, so it needs 4 electrons, right? So carbon can fill up, or can do all sorts of single, double, triple bonds. A single bond looks like this. We represent it with just that one line, so that is a single bond. Okay? I could also do this. That is called, it has 2 lines, so you can probably guess that's a double bond. And then if I wanted to, it could triple bond to something. I'm not going to draw that one just because I'm not really sure off the top of my head what I should draw. But they can technically have a triple bond. Okay? So let's take a look at page... I guess page... No, let's stick with page 8 for now. Sorry about that. So the more of these bonds, or the stronger your bond is, the more bonds you have. So this double bond, this 2 bonds, is stronger than a single bond. A triple bond would be stronger than both of these 2. But the idea is that you have to share enough in order to fill up your ring. So you'll never see this. So even though I drew it, this is not real. Why? Because I told you carbon needs 4 electrons, right? So if carbon needs 4 electrons, but over here I'm only bounded to 1 H or 1 electron being shared, that means I still need 3 more. There's no reason for carbon to do that. So what happens is that in real life you're going to see something called this, and this is the most basic one. You're going to have a single bond to 1 H, 2 H's, 3 H's, and then a 4th H. Alright, and this is going to be something you'd actually see because it covers the 4 electrons. 1 electron, 2 electrons, 3, and 4 electrons. Okay, so the idea is that carbon needs 4 electron bonds. Whether or not it gets them out of single bonds or double bonds doesn't really matter. We'll talk about that soon. So if it was double bonded, it would look something like this. So carbon, there are 2 electrons taken care of here, right? We still need 2 more for each of these. That means that each of these things has to be attached to a couple of H's. Alright, because there are the 2 in the double bond, but you still need 2 more for each carbon. Each and every element needs its own number of electrons, so even if I have 2 carbons, I still have each of them needing 4 total. These are shared, so right now this one has 2, that one has 2. Add this, now this one has 3. Add this, now this one has 3. We still have to cover the other 2 that this carbon needs. Okay? So the only reason that elements bond together is because they're trying to fill their shells. Let's go ahead and move on to page 9. Just take a look at the example, page 9. Feel free to read it over. I'm going to read it with you guys. How many pairs of electrons does a carbon atom share with each hydrogen atom in the chemical compound methane, which has the formula CH4? So you'll notice that I drew one of these shapes with a C in the middle, and then an H, 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 H. So that's CH 4 times because there are 4 H's there. And it's asking us how many pairs of electrons does a carbon atom share with each hydrogen atom. What kind of bond is this? It's a single bond. Therefore, it only shares 1 electron. So each hydrogen shares only 1 electron with the carbon. If this were instead of double bond like it is over here, then this would be a 2-pair thing. If there was, I don't know, you could technically have like, I don't actually think you'd have a quadruple bond, actually. Just kidding. So you won't have a quadruple bond, so that last answer, 4 pairs, is just not going to happen. But that is the idea. All right? So we're going to go ahead and move on. Let's go ahead and check page 10. Hydrocarbons. Okay. So hydrocarbons are a separate class, which you guys have seen here. Like, this is what I'm combining together. Hydrocarbons are literally, let's see what's going on here. Hydrocarbons are the combination of hydrogen plus carbon. That's literally it. You're just mixing hydrogen and carbon together in different proportions. So sometimes you'll have more H's, less H's, more C's, less C's, that kind of thing. And you're going to have all kinds of bonds in them. All right? But we're going to give names to these bonds. So if you have single bonds, double bonds, and triple bonds, whatever it is that you're making, these hydrocarbons are going to have different names. They're going to end with this. So this one's always going to end in ANS. Okay? Double bonds are always going to end in ENES. And triple bonds are always going to end in YNES. How this would be pronounced is that you have something like, this would be an alkane. With a K, if I'm not mistaken. This would be an alkene. And this would be an alkyne. So what's going to happen on your mastery test is they're going to introduce, get that on screen, they're going to introduce to you several different kinds of things, and they're going to give them weird names. They're going to be like penta something, 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 something. But if it says something ene at the end, E-N-E, you know that there's a double bond in there. So you don't need as many hydrogens as you would in alkane. Okay? So if you see that A-N-E, you're going to have single bonds. You're going to need lots of hydrogens. If you see that E-N-E, you're going to have a double bond. You get less hydrogens. And if you see that Y-N-E, you know you have very few hydrogens bonding up to your carbons here. Okay? So let's see if we can't get an example on page 11. Alright, just kidding. There's going to be a whole lesson activity. Let's try page 12. Okay, they talk more about how to name these things, and they go through a couple. If you look here, they tell you that hydrocarbons with 1 carbon have a prefix of meth, so that is like methane. Alright, so if you have 1 carbon, it's going to be a meth something. So you guys have probably heard of this in methamphetamines or crystal meth, that kind of thing, is based off of these carbon structures. So methane is that very basic C wrapped with 4 H's that you saw, because it only has 1 C in it. However, if you saw something like methene, it would not have 1 C. It would, or I'm sorry, it still has 1 C, but this is methene, so it has a double bond somewhere. Okay, so that means that it would be mixed up with something else. I don't know exactly what, because methane's not really a real thing. You're just never going to see it around. So that doesn't really exist. But that's the idea. You can take the same name and just add a different ending. This changes how this would look. It would look like C mixed with something or another. I'm honestly not really sure, because like I said, it does not exist. Alright, neither does methine. Neither of those actually exist. We're gonna go ahead and move on. Oh, so meth was 1C, but you'll see that they also tell you that so like ethylene, I guess would be the three types. Again, they don't all exist. You've probably heard of ethylene because it's in corn, or they use corn to create ethylene like crazy, but um, the other forms of it don't actually exist. Like ethylene is not a real thing, just like methane and methine are not real things. They theoretically exist. They also give you three as prop, like propane, and four is like butane, and five is pent, but I honestly don't know. I guess pentane would be the name of it. I don't really know what a pentane is. Okay, so let's go ahead and move on to page 14. And it gives you a bunch of examples here, and it's going to teach you how to work with the words. So let's take a look at this one just as an example. You'll notice that for all of these, it changes the words, the prefixes, and the proteins. They're all based on that ETH. All right, except for cyclopentane. That's a little different because ETH is in pentane. Well, whatever. So methane. Meth, I told you, means we have one C. So if we look through this example, how many of them have just one C? It looks like, scroll. Alright, sorry, I gotta maximize my page here. But if you take a look at this picture, you'll notice only one of these has one C. That is the methane. Okay. I also showed you that very basic structure earlier when I drew it here, so it looks something similar to this shape over here. Okay. Ethine. All right. So that YNE. I told you that YNE means you have a triple bond. So I want you to take a look over here. Which one has a triple bond? All right. So if you were paying attention, you probably found the one that looks like it has two carbons, and there are going to be three little bar things bent and attached to each other. All right. Now let's take a look at ethene. So E-N-E. Just remember that that E-N-E ending means that you have a double bond. All right. You have a double bond in your carbon whenever you have that E-N-E ending, which means we're going to look at the carbons, and we're going to look at the one that has two little bars attached to it. All right, so that is going to be your ethene. And then your cyclopentane. First off, cyclo means a circle, so you can probably guess which one kind of looks like it's connected in a circle. Further, pentane, pent means five, right? So you have five over there. So that's going to be your pentane. It's also that A-N-E ending, which means it has all single bonds. All right, so only two of these have single bonds. You already used one of them for methane. The other one was cyclopentane. So that's how to work through these kinds of problems. It is not easy. You do have to get used to the words. So ANES or ANE, single bonds. ENE, double bonds. YNE are triple bonds. All right. So let's go ahead and move on to page 15. All right. 15 and 16 are going to talk about structural and geometrical isomers. Essentially, isomers are just the same hydrocarbon, but they exist in different forms. It's kind of like when I taught you guys what isotopes are. Isomers are like different forms of a whole molecule. So I told you guys that carbon has a lot of isotopes, like C12, C14, C13, etc. All of these are isotopes, right? Because they're only C, they're only carbon. You could have this technically for any element, like oxygen, and you could have like O6, O7, O8, or something like that. But it's only one element that we're dealing with at a time. So we're only dealing with carbon here, you're only dealing with oxygen, you're only dealing with, gold or whatever else it is. But isomers are different in that you'll have something like this. C, and then wrap to H, and then connected to more C's, and something like that. And then all of these will be connected to H's. So H, bars. Don't forget your little bonds, just because, and that kind of thing. So this is one type of hydrocarbon. But similarly to this one, I don't necessarily have to have it looking the same. I can change it. I can take my C's, and instead I'm going to take like this C and some of these H's. I'm going to create something called CH3. Okay? So I'm going to make CH3. That's still the same amount, but it's just a very different It's a very different looking structure. So if you've got your tutorial open, you can see this a lot better, but I told you I'm going to move one of my C's. It's no longer going to be bonded at the end here. What's going to happen is I'm pulling out that C and the three H's, so right here, taking this whole thing, and I'm going to combine it together right here. I'm going to call it CH3. Okay, so I took a C and its H's. It still is the same number of stuff. It's just a now, so let me connect these to a bunch of H's. Connect these to a bunch of H's. Hold on one sec. This one is just going to have an H up here. H. So if I were to write this whole formula out, this is C 1, 2, 3, 4, H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh wait, sorry, C4, H10. And if I count these up again, 1, 2, 3, 4 C's. Can you see this? No, sorry, I was at the bottom, my bad. So let me zoom in. Okay, so I told you guys that we were working with these two structures. You probably see them in your tutorial. But if you count up your H's, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 H's and 1, 2, 3, 4 C's. So that is C4H10. This shape down here, clearly different because I took this whole ending part, all these CH's and whatnot, and I moved them down here because it's 1C, 3 H's, 1C, 3 H's. It's still the same thing. So I'm going to count them up. 1, 2, 3, 4 C's. All right, 4 C's. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 total H's. It's still H10. So it's called an isomer because when you write out just the molecular formula, C4H10, C4H10 looks exactly the same. But it's different in that something has changed in the actual physical structure. That is why this is an example of a structural isomer. Okay, so everything I just drew was a structural isomer because I literally, the formula is still the same. I just structurally took a chunk of it, combined it together, and I put it somewhere else. That is going to be a structural change. All right, so I combine things. Normally with a structural change, it's either going to be me going from here to here or from here to here. I'm either going to combine something or I'm going to take it apart. All right, and that is what makes it a structural isomer. If you go on to page 16 of your tutorial, you're going to see another set of isomers. And they're going to use much simpler ones. I actually like these a lot more as an example. Let's go ahead and talk about these geometric isomers real quick. What's going to happen, let's see, let's make sure this is all on camera. All right, cool. So you have geometric isomers. H3, H3C, bonded to carbon, bonded to hydrogen, double bonded to another carbon, and then bonded to another CH3, and H down here. So here is your original thing. Keep in mind your chemical formula is going to be 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. All right, C4H8. Okay, we are now going to do the other form. You don't have to worry about these words that they use. They use cis form and trans form. I don't really care. All it's really trying to say is that this is the naturally occurring form. You have a transform or a transform version that like it switches around. So take a look at this. What's going to happen between these two images? The difference is all the things on the right are going to stay the same. So C still bonded to CH3, still bonded to C. But what's going to happen is that on the left of this double bond, these two things are going to flip upside down. Okay, so we're just going to flip them. So instead of H being at the, there's a C. Instead of H being at the bottom, we're going to have H3C at the bottom, and instead of H3C being on top, we're going to have H on top. So the difference is that the left side of this thing flipped. You'll notice that I did not take anything apart. Nothing broke apart into a bunch of little H's or a bunch of little C's. Nothing got put together into any bigger thing. So the difference between a structural isomer is that you normally have a breakdown or a creation. So you either bond things together or you break them apart. All right. So that's a structural isomer. But a geometric isomer is literally the same thing. It's just that there are going to be two things that, or I'm sorry, there are going to be some things that flip. So I could have flipped this right side, not in this example, but it's possible that the right side flips. It's possible that something from this top right spot will move to the top left. But a geometric isomer is still exactly the same. It's still that. Where'd my blue pen go? No matter which one you look at, it's still an X shape. It's still an X shape. Okay? It's still 1, 2, 3, 4 C's, 5 C's. Did I miscount? 1, 2, 3. Oh, my bad. This is supposed to be an H. I just miswrote it. But it's still 1, 2, 3, 4 C's, and then still 1, 4, 5, 6, 7, 8 H's. So it's not like the formulas change. Just like with a structural isomer, remember that's a big deal. The actual formula doesn't change. In structural isomers, you normally break something down, or you either go and you break CH3 down into all that, or you go from that and you combine it together to get CH3. You break down or combine. With geometric isomers, on the other hand, all you're doing is flipping some stuff. Okay? You're moving stuff around. All right. Hopefully that made sense. I know that's a really hard lesson. Excuse me. I know that's a really hard lesson, so do let me know if that gives you trouble in the future. So 18 is the summary. So now we're going to talk about my summary real quickly. I'm going to go over the things that I think are going to be most important for your test. So here's going to be that 5-minute review that I promised you guys. All right. So you do need to understand how many pairs of electrons are going to be shared amongst carbon atoms. Okay. And remember that every carbon needs 4. So if I give you an example of, if I tell you that you have an alkyne, okay, you have like methane, butane, ethylene. You have ethylene, okay, ethylene. What that means is that ENE means that you are going to combine and double bond 2 of them. So here are 2 C's. We're going to double bond them. All right, because it is an ENE ending. If it was an ANE ending, it would only have a single bond. If it was a YNE ending, it would have a triple bond. But in ethylene, there is a double bond between the carbons, right? That must mean that we need how many more H's? So we're already sharing 2. Each of them need how many more? They needed 4 more. So remember, carbon is tetravalent, so they needed 4 total. Each of them has 2. That means that we must need 2 more. So you're just going to tack on a couple of H's like that. Okay? So when you get questions like that, all you have to remember is that you started off with 4. You need 4 more bonds. Every carbon needs 4 more bonds. Okay? However you have to make it. So if you remember your ANE, ENE, and YNE, you should be good. Let's see. What else do you guys need to know? Alright, remember isomers have the exact same number, same formula. So all isomers, C4H10, C4H10. It's not like the molecular formula changes. Alright. Okay, there's going to be a question on your test, and I'm actually going to just give you this one because I didn't actually explain this, and I don't have any materials for this one. I don't want to explain allotropes because it probably should have been explained with isomers. Allotropes are going to be different structures because of different arrangements. So like my carbon atoms could be all over the place, okay? And that is what an allotrope is. Just keep in mind, you're going to get a question possibly on your mastery test where it asks you about how coal and diamond are similar. Just remember that they are allotropes. That word is A-L-L, or actually I'll just write it out here. That word is allotropes, A-L-L-O-T-R-O-P-E-S, allotropes. Okay, so there's that word. What else? So you guys remember carbon is tetravalent, so that means that it needs 4 electrons to fill up its shell. So structural and geometrical isomers, I told you guys that was important, so you are going to have to pay attention to the other 5-10 minutes of this video, however long it took me to explain these isomers. Okay, so that's that. Okay, I've covered everything on the exam, so the main things that you need to worry about that I went over, you know what, maybe I don't really have a 5-minute review. It was all kind of important. Unfortunately, if you don't understand anything, or if you don't understand the things that I put in this tutorial, you're gonna have a lot of trouble with this mastery test. Let me know if you need help with it. We can definitely work it out and whatnot, and I can definitely talk to you. So just message me, and we'll try and work it out. I'm sorry that this didn't make more sense, but I wasn't sure how to teach this if you guys don't have a background in chemistry. Normally, kids in biology have some kind of experience from physical science or whatever. So this is actually a pretty hard lesson as far as our biology class goes. So again, just message me if there's any major issues with it, okay? Because I don't want to keep this video going too long. I could go back and go in detail, but this is really, to learn all this would be about an hour and a half lesson. So we've cut it into 30 minutes. Hopefully it made sense. Let me know if you need anything. All right, guys. Sorry this one was all over the place. Hopefully it still helps. And I'll see you guys next video. Bye.